next speaker is Andrew Read-McFarland from Denison University. Andrew's been working with Professor Main at Denison, and he'll be discussing numbers and the heights of their happiness.
I'm Andrew Read-McFarland, and I'm doing research on numbers and the heights of their happiness. So we're going to be talking about a happy function. We're going to let that be called S. So a happy function is a function that maps a positive integer to the sum of the square of its digits. For instance, S of 14 equals 1 squared plus 4 squared, which is equal to 17. It's well known that that after repeated iterations of S, every integer will either map to 1 or 4. You can see this by seeing every number greater than 100 is going to decrease after application of S. And you can exhaustively check every number less than 100 and see that it occurs. You can see that S of 1 is equal to 1. So we call that a fixed point, but 4 is in a cycle of 8 numbers, so we call that a cycle. Since 1's a fixed point, that's why we call it special. I guess it's a happy number. So a number that has repeated iterations of S equals 1 is a happy number. If it goes to 4, it's not a happy number. So a happy number has height h if h is the minimum number of iterations of S required to yield 1. So for instance, 10 is a height 1 happy number because S of 10 equals 1. And 13 is height 2 because S of 13 equals 10, and S of 10 equals 1. So it takes 2 iterations of S. We define 1 to height 0, even though S of 1 equals 1. So we're going to let sigma h denote the smallest height h happy number. So sigma 1 is 10, and sigma 0 is 1. So I just mentioned there, what are the smallest height h happy numbers? Gremlin and Teeple in 2003 explored this concept, and they found the smallest height 0 to 10 happy numbers. And they're kind of fun. So, does anyone see anything interesting about this chart?
What's up with 7?
That's one very specifically. It's you know, you can kind of see why 1 goes 1 and 10, then something. Height 5, 7's there, and then boom, gets really large, real fast. So one thing I was thinking is, wouldn't it make sense that S of sigma h plus 1 equals sigma h? You know, add the smallest one of a height, go to the smallest one of the last height. Because you have to see that a height, say 7 number, has to map onto a height 6 number. But this is not always the case. As you can see here, the height 6 number is 356, but S of that is 70, not 7. And you saw that after height 6, sigma h becomes very large. You can see those numbers, massive. And they end with tons of nines. So I was looking at ways we can find bounds to know what sigma h might be. And I had, in an offhanded remark, my advisor mentioned this theorem that every integer is the sum of 4 squares. So for instance, 7 is 1 squared plus 1 squared plus 1 squared plus 2 squared, and 56 is 0 squared plus 2 squared plus 4 squared plus 6 squared. This was not proven until Lagrange proved it in 1770. So the inventor was like, hey, maybe this is the case, and Lagrange was like, yes, it's true. Then right after Lagrange proved this, Brain was like, that's not good enough. Maybe we can show it for more than just power 2. Maybe we can show it for every power. So there's every number system of 9 cubes and 19 fourth power integers. And it's hypothesized that for higher exponents, there was also some number. In 1909, Hilbert proved that there was a number, but he didn't tell us what it was. He didn't know. And then in 1920, Harding Littlewood gave a closed form for g of u, where g maps the exponent to the numbers. So g of 2 is 4, and g of 3 is 9. And it works for all, but at most finitely many. So using this, I found that sigma h plus 1 has between sigma h divided by 81 and sigma h divided by 81 plus 4 digits. This is because no digit can be more than 9, and 9 squared is 81. So it must have, sigma h must have at least, sigma h plus 1 must have at least sigma h divided by 81 digits. Because if you're saying mapping to a billion, you have to have a billion divided by 81 at least, because each digit has to have, if you have a bunch of 9s, each 9 is going to be 81. So you need that many. If you have less than that, then how are you getting to that number? And sigma h plus 1 can't have more than sigma h divided by 81 plus 4 digits, as the remainder can be expressed as the sum of 4 squares. So for instance, if you're mapping to 200, you can put 2 9s in, and that gives you 162. And that remainder can be expressed as the sum of 4 squares. And each of those squares has to be less than 9, because that's the remainder after 81. So when does sigma h plus 1 equal sigma h? So we're going to let tau h denote the second smallest happy number of h. So only smaller h happy number is sigma h. If there's a large enough gap between sigma h and tau h, then sigma h must map to sigma h. Sigma h plus 1 must map to sigma h. And I have specific bounds for this gap, but it would not be constructed to put it in the presentation. To guarantee this gap, it is actually sufficient to show that sigma h ends with 3 9s and maps to sigma h minus 1, or simply that sigma h ends with 4 9s. The previous example, you can see that sigma 7 has 3 9s, and it maps to sigma 6. So sigma 8 must map to sigma 7. So you might be saying, okay, that's cool, but does sigma h always have 4 9s after a certain point? It might seem intuitive like that, because if you're mapping to, say, a billion, why would you have 8s when you could have 9s? Because 8 only contributes 64, 9 contributes 81. And this is the case. Larger than a certain bound, based on the base, it will end in 4 9s. In base 10, I believe you need larger than 10 to the 23rd, which sigma 7 already is. So by putting this together, if sigma h is sufficiently large, then sigma h plus 1 is equal to sigma h. Now, I've only been talking about base 10 with exponent 2. But this is actually, I didn't really use many properties of base 10 or exponent 2. So we can generalize it for all bases, because the only property I used was the maximum digit of a base. So for instance, in base 8, 14 is represented as 1 6, and s of 1 6 is 1 squared plus 6 squared, which is equal to 37, which is 45 in base 8. So you can see that it modifies what numbers you'll get out of things, but there's nothing really intrinsically special about base 10. So we can generalize it further by having s not just do squares of digits, we can go to cubes, to the 4th power, and so forth. And since sum of 4 squares theorem is generalizable for all exponents, I can modify that theorem as such. So for instance, s of 3 of 14 equals 1 cubed plus 4 cubed, which is equal to 65. And I also have been talking about mapping only to happy numbers. But I actually didn't use any fact about 1 being a fixed point or just being 1 at all. So I'm going to use a definition called U-attracted. The number is U-attracted if repeated iterations of S equal to U. So for instance, 13 is a height 1, 10 attracted number because S of 13 equals 10. So we'll let sigma h of U denote the smallest height h U attracted number. So by putting all this together, for any base b, exponent e, and integer u, once sigma h plus 1 becomes large enough, it will always map to sigma h. Thank you. Any questions?
Okay, questions for Andrew?
Yeah, go ahead.
How did people decide to start calling these numbers happy numbers?
I think it came from this, one of the first papers on it. They actually generalized it for all bases. It's called generalized happy functions. And they said if a number eventually goes to 1, it is called an e power b happy number, which is kind of funny. I think that's why they decided, it's cool because 1's a fixed point, and it's nice if it goes to 1, whereas 4 is not. It goes all around too much. Yeah, go ahead.
So in base 10 with squares, all the numbers always go to 1 or 4.
Yes.
Are there any cases like bases or exponent situations where the values don't actually approach anything? Maybe they're like all up to infinity or something?
No, in every base, everything will always, some things will always go to 1. For instance, base 2, everything's happy.
Okay.
But there are some cases like in base 7, there's like 3 fixed points and then 2 cycles. But every number will either go to fixed point or a cycle. The worst case is every number is a fixed point. Go ahead.
Was there any effort to figure out, you say sufficiently large, right?
Yeah, I have an explicit bound on that sufficiently large, depending on the base and the exponent.
Oh, got it, okay.
And GV.
For that second bullet point, I'm just trying to understand your wording.
Oh, sorry. Height 1, 10 attacking number, right?
Okay, those, the 10 and the 13 are reversed.
Yeah, so sorry. 13 is the height, 1, 10
10
attacking.
attracting number, okay.
Okay, let's thank Andrew again.